In this video, we're going to look at the different types or sets of numbers that exist. This way, when someone says the real numbers, for example, you'll know exactly which numbers we are and aren't considering in our answers. So here we have a listed tree of the different sets that we'll be working with in this class. And even though it's kind of built looking like it's going vertically down, I actually like to identify most of my answers by starting from the bottom row and then working my way up so that I can talk about which numbers are being added rather than which numbers we're removing as we go down. One comment along those lines is that if I say a number is in a set, like if I say a number is in this set here as 3, then it's also in this set, and this set, and this set, and this set, but never jump horizontally to some of the other sets I have listed here. You'll only include the ones that have connecting branches going vertically up the tree like that. So there is actually a set that exists below the whole numbers, but it's essentially the exact same as the one I have listed here. It's called the natural numbers, and it's all of these whole numbers that you see, but it excludes the number 0. I didn't include it on here because it doesn't come up that often, and because it's essentially the same as this one. They're functionally the same in most cases. So if you need to exclude 0, there is one called the natural numbers. So for our purposes, I'm starting here with the whole numbers. This only includes these numbers 0, 1, 2, 3, 4, 5. These are also often called the counting numbers because we're not considering anything like the decimals and the fractions that exist between them, nor are we considering anything like the imaginary numbers that we'll get to up here when you take the square root of a negative number. So whole numbers means just those whole values, none of the decimals and fractions in between. When we go up a level here, we hit the integers. Now we're including the negative numbers as well. So now not only do we have positive 1, but we also have negative 1. Going up again, this is actually one of the most important and biggest sets for our class. The rational numbers are any numbers that can be written as a fraction. Now, a couple things that can be confusing about this are even numbers like 0.5. They do count as rational numbers because we know that we can write this decimal as the fraction 1 divided by 2, or 1/2. So many numbers that aren't written in fraction form are still considered rational numbers. And that's why even the integers and the whole numbers are considered inside of this set as well, because I could write something like 4 over 2, and that would be the integer 2, which is in both of these sets. Sometimes the best way to describe the rational numbers is to look at what is not considered rational, so the irrational numbers. These are your infinite, non-repeating decimals. There is a such thing as an infinite repeating decimal, and we usually indicate those by putting a bar over some of the numbers to indicate that it's going to do 2, 3, 2, 3, 2, 3, 2, 3 forever and ever. So that would be an infinite repeating decimal. That means that those numbers are actually included here in the rationals. It has to be a non-repeating, so you can't be able to put a bar over a couple of the digits to indicate an irrational number. Some of the most common examples are numbers like pi, the 3.14 that you guys have worked with a lot. You may or may not have also seen this number e. This is another number just like pi. It's an infinite non-repeating decimal that has a very specific value. But also any non-perfect squares, those actually make infinite non-repeating decimals as well. So square root of 2, square root of 3, and square root of 5, those are irrational. Square root of 4, since that's a perfect square, that would actually be equal to 2. So that number would actually end up being included in all of these sets over here instead. So only the non-perfect squares. Next, if we group together both the numbers that you can write as fractions and all of those infinite non-repeating decimals, then we have what we call the real numbers. This is also a very important set. This is one that gets used a lot. So we still have the numbers like pi, we still have the whole numbers like 7, and the infinite repeating decimals like 8.23. And you'll notice that I wrote a math symbol here that says a plus 0i. That's because if you look at the very biggest set of complex numbers, usually there's a number in both of these a and b spots, and the I stands for an imaginary number. Well, if you don't have an imaginary number, then you only have the a value. That's what I'm indicating here. That's what makes it a real number. If you look back at the complex numbers and you imagine putting 0 in for this spot instead, this is the real part of the complex number, then you end up with a number that only has a number times I. So now what you have is what we call an imaginary number. These are either written with an I in them, or they might still have the negative symbol inside of a square root. That's what creates the imaginary value, is whenever you have a negative inside of a square root. So whether they have the I or they have the negative inside the radical, that's a pure imaginary number. And then if it has both, So that number might be written as something like 2 plus 3i. Then it's neither pure real, nor is it pure imaginary. It's complex when it has both the real and the imaginary part. So now let's look at a couple examples so that I can show you the process for identifying if your answer is a natural number or an imaginary number, whatever the case may be. So starting with number 1, the directions say identify the smallest set of numbers that each example belongs to. Well, I have the number 1.2, which I know occurs between 1 and 2. If I look back at my set of numbers, whole numbers do not include the decimals and fractions in between, so it's not one of these. Same thing for the integers, because that just included the negative numbers, so I still am not including the numbers between 1 and 2. But here I'm going to stop. Many decimals can be written as fractions. In fact, I'm going to show you how to write this decimal as a fraction. All you need to do is take the digits you see, ignore the decimal place, and write that number out. Then divide. If there's one number after the decimal place, divide by 10. If there were two numbers after the decimal place, you would divide by 100. If there were three numbers after the decimal, you would divide by 1,000. Basically, however many digits come after the decimal place, that's how many zeros you write. So no decimal on top, number of digits after the decimal, that's how many zeros on the bottom, and then reduce that fraction. If I reduce 12 divided by 10, I get the number 6 over 5, and you can test this in your calculator. 6 over 5 is equal to the decimal 1.2. So since we were able to rewrite 1.2 as a fraction, and that's what rational numbers are defined as, numbers that can be written as fractions, then we're able to say that the answer to number 1 is a rational number. So now for number 2, again, we want to identify the smallest set of numbers that this example belongs to. So again, I'm going to start from the lowest branches of the tree and work my way up. I don't have 5 listed here in this bottom branch, but the pattern I'm indicating is that this is all of the positive whole numbers that you have worked with. So 1, 2, 3, 4, 5, etc. So 5 is a whole number. And also just to point out, again, if this question had not said what is the smallest set, but if it had said all of the sets it's included in, then 5 is not only a whole number, it's also an integer, and a rational number, and a real number, and a complex number. But since this example just says what is the smallest set that it belongs to, we're going to write that this is a whole number. Okay, and now for number 3. So here we have a square root of 7. The most important thing to pay attention to on the square roots is will the number come out as a perfect square or a non-perfect square? So can you break down the square root of 7 in some way nicely so that there's no radical left over? So square root, it's not a whole number, it's not an integer. Basically, we're trying to figure out if it comes out to one of these cases. Is it an infinite non-repeating decimal? And I told you that the non-perfect squares, that's what's included here in the irrational numbers set. So the smallest set it belongs to is the irrational numbers, but it is also a real number and a complex number. So number 3 is irrational, and then for number 4, now we have to be very careful about the negative symbol on the 13. So this is a negative 13. It's not a decimal or a fraction in between integers, but it is a negative number. So let's see how that affects the different sets. Since the whole numbers only include the positive ones, basically we just have to jump up one step here. Now we're including the negative integers. If it was a negative decimal, I'd have to go up another step to the rational numbers. But for a negative whole number, essentially, we're going to call this the integers for the smallest set. Now we're getting into some of the less common numbers, the ones that have eyes on them or the square roots of negatives. So these imaginary numbers, this is kind of on a different branch of the number tree entirely. So you can ignore all of these. You can just keep working your way up. The eyes don't come into place until you get all the way over here on the imaginary numbers. So the main thing we need to look for on anything with an eye in it is it just an imaginary number by itself, or does the number have both a real and an imaginary part, in which case we would call it complex. So this one only has a number times I, the number being 1, since I don't see a coefficient on it. This one has both a real number, 4, and an imaginary number, 2i. So that's the difference I was referring to on the tree here, the pure imaginary numbers and the complex numbers, which include both parts. So that's what gives us our final 2 answers here. So again, there's not much work to do on identifying the smallest set or all of the sets that a number might belong to. This is really just more a definition thing, making sure you guys understand which numbers to consider when we talk about the whole numbers, the integers, the rational numbers, etc. And that's it for this set of notes. Thank you.